Hi everyone, I'm Joy. I hope you are all safe and healthy, and I am sending you my love from quarantine. Today we're going to be talking about information cascades, and this is the first chapter in a new section, so I do want to take some time to explain the motivation. As you know, this class is about networks, right? And this chapter proceeds with the idea that people in a social network can influence each other in the behavior and decisions that they make. And as you can imagine, this influence comes in many forms. You can influence people through the opinions that you have, the products that you're buying, the brands you support, the technology you use, the political positions you identify with. And networks can take this individual behavior and these individual preferences and aggregate them to produce population-wide outcomes. And one of these outcomes is mass imitation. Networks can cause people to imitate each other on a very large scale. And the question this chapter tries to answer is, how does this occur and why? What is a rational explanation for this kind of imitation? For a quick outline of what we're going to be talking about today, we're first going to start off with some examples of information cascades and just define it a little bit more carefully. We're going to talk about a classic herding experiment involving a bag and 3 balls. We're going to use Bayes' rule and conditional probability to explain the results from this experiment. We're going to then use Bayes' rule to develop a general model for information cascades, and we're going to apply this model to understand how people make decisions in sequence. So, to kick it off, let's say you are on spring break, you're on a road trip, you're driving along the freeway, and you are hungry. So you decide you're going to take the next exit off and go to this unfamiliar town to have dinner. You search up available restaurants on Google, and you come across restaurants A and B. And, as you're doing your research, you're looking at, what's the menu like? What kind of food do they have? What is the ambiance? You decide that restaurant A, menu looks great, food looks great, that's where you're going to go eat. But then you get there, right? And what you see is that restaurant A is completely empty. There is literally nobody eating inside of restaurant A. Inside of restaurant B, however, there are tons of people. It's super busy, it's hustling and bustling, it looks like people are really enjoying their food. So now, you're faced with the decision. Where are you going to go eat? You did research before, right? And we call this research your private information. Based on your own private information, you would want to go to restaurant A. You looked at the menu, you looked at the pictures, everything looked great. Based on your private information, restaurant A is the best choice. But probably intuitively, something is pulling you towards restaurant B. And how do we explain this? Well, if you believe that the other diners in this restaurant, if they have similar preferences to you and that they've come by their information independently, then maybe the information you can infer from their choice to go eat at restaurant B, maybe that information is more powerful than your own private information, right? And what is that information? It's that the food is good, or maybe it's just a really awesome restaurant. You don't know exactly what these diners know, but based on their behavior, you can infer some kind of information and weigh that against the private information that you had coming in. So ultimately, if you do decide to go to restaurant B, abandoning your own private information, we call this an instance of an information cascade developing, or herding, right? And what's been going on here? To untangle this a little bit, first, information cascades can occur when people make decisions sequentially. In this case, you made your decision of where to eat after all of the other diners have already picked where they want to eat. Second, later people get to watch the actions of earlier people. In this case, you can see what everyone else is doing. And third, based on these actions, later people can infer something about what earlier people know. You don't know exactly what these earlier people know, but you can see what they're doing and make inferences to increase the amount of information that you have. So this is an information cascade, and this is a form of imitation. However, you might think that an information cascade isn't the only reason why an imitation can occur, and you would be right. There are plenty of reasons why people might imitate each other, and not all of these can be explained through information cascades. And I'm going to better flesh out what exactly an information cascade is by comparing it to kinds of imitation that we are not interested in today. And the first is the social pressure to conform. So if you've taken an intro psych course, you're probably familiar with Stanley Milgram and his experiments involving social pressures. In one of them, he had a group of experimenters stand on a street corner and look up at the sky, and then he would observe what passerby would do. What he found was that when there were only one or two experimenters standing on a street corner and looking up, very few passerby would stop. When he increased the group size to 15, almost 50% of people would also look up at the sky. Milgram explained this by naming the social force for conformity, right? The social pressure to do what other people are doing. And he said that as the number of people participating in this activity increases, our desire to also fit in increases as well. And this is kind of, a psychology explanation for what's happening. If we take the perspective of this chapter of rational imitation, there might actually be a very good reason to look up, right? Maybe this is an information cascade. You don't know what all of these experimenters looking up at the sky know, but if you believe that they have some kind of information, you can observe their behavior and reasonably infer that maybe there is a good reason to look up at the sky, and so I should look up at the sky too. So this chapter, an information cascade, is strictly rational. And the truth is, most decisions, most forms of imitation involve both rational and non-rational reasons, right? Everything from fads to fashion, from, who you're voting for to adoption of technology, all of these can be seen as examples of information cascades, with some other factors combined as well. Within rational imitation, though, there is a difference between information cascades and other forms of rational imitation. And one of them I want to draw your attention to is between informational and direct benefit effects. Informational is for information cascades. Direct benefit effects is what the next chapter is about. So if you are rationally imitating the behavior of other people, why might you do this? Well, the first is because you're making inferences based on other people's actions, as you do in an information cascade. The second reason is because by imitating other people, you benefit directly. What does this mean? The classic example is with fax machines, right? Fax machines are completely useless if nobody owns one, but if everybody has one, you probably also want a fax machine because then you can go around and fax everybody. And the more people that have fax machines, the more you having a fax machine is worth to you. The analog today would be something like email or a social networking platform. The way this works technically is because the payoffs are changed by other people. With informational effects, your payoffs are influenced indirectly. Other people change the information that you have based on their behavior and what you can observe from their behavior. With direct benefit effects, other people's behavior changes your payoff directly. When people buy a fax machine, your payoff increases. But as with the previous example of people standing on a street corner, most decisions and most forms of imitation involve both of these rational effects, right? And they can actually either both work positively in your favor or one can work positively and one can work negatively. If you think about technology adoption, let's say with Instagram, if everybody is getting Instagram, informational effects tell you, oh, maybe there's something really awesome about Instagram and that's why everybody's getting it. And that increases your payoff to getting Instagram indirectly because you're observing what other people are doing. The direct benefit is, wow, everyone's using Instagram. So that means if I go on, I can connect with everybody that I love. It can also have the opposite effect. If you think back to the restaurant example from the beginning of this presentation, the informational effect we established was that other people eating at that restaurant maybe tells you how good the food is, how it compares to restaurant A, something like that. But the direct benefit effect is actually negative. If everybody's eating at restaurant B, you have to wait there for a longer period of time. So now that we've established what is not really part of information cascades, let's name the components of an actual information cascade. First thing, there's some kind of decision to be made. Second, people make the decision sequentially and you get to watch what earlier people have done. Third, you have some kind of private information that can help you make this decision. And finally, you don't know exactly what the earlier people know, but you can observe their behavior and then make inferences about their private information. And you can use this information to then help you make your own decision. So the fundamental idea is when you make decisions based on what other people do and not what they know. And this makes us ready to move on to our experiment, the classic simple herding experiment. conducted by Anderson and Holt in the late 1990s. So the setup for the experiment is like this. You have a bag at the front of the classroom with 3 balls inside of it, and you have a very long line of students. You don't know the composition of this bag. There's either 2 red balls and 1 blue ball, which we will call majority red, or there are 2 blue balls and 1 red ball, which is then majority blue. The goal is for the students to guess what color or what composition the bag is, whether the bag is majority red or majority blue. And how does this work? So each student, one by one, is going to come up to the bag, draw a ball, look at the color, and without showing it to the rest of the class, put it right back into the bag. And then they're going to make their guess and publicly announce it to everybody else. They're going to guess whether it's majority red or majority blue, and the students come up one by one. This is like the beginning example because there are students making decisions sequentially. There's a decision to be made, right? Like whether this bag is majority red or majority blue. They make this decision in sequence. They get to see earlier people's behavior. They get to hear the guesses, but they don't know what the earlier people's private information is. They don't know what color the ball was. And they each have their own private information, the ball that they drew. So this is the perfect setup for an information cascade. And let's go through and analyze what each student does to see if that actually happens. If you were student 1, you are going to draw a ball from the bag, and it's a pretty simple decision rule, right? If you draw a blue one, intuitively, you should probably guess that the bag is majority blue. If you draw a red one, majority red. So it's a very simple decision rule, just guess what you see, and as a result, everybody else in the line, assuming that person 1 acts rationally, knows that their guess conveys perfect information. That's important. Their guess conveys perfect information. And for the sake of this example, let's just assume they saw blue and guessed correspondingly majority blue. Now let's say you're the second student, right? You can come up and draw a blue ball. That's very easy. You've heard a guess of blue, you get a blue ball, you should probably also guess blue. Let's say you draw a red ball, right? If you get the opposite color, you know that the first student's guess conveys perfect information. So they drew a blue ball, and now you've drawn a red ball. So essentially, you're drawing twice from the bag, and so you should be completely ambivalent to either guess. And let's just say you break the tie by guessing what you see. So again, the second student's guess conveys perfect information. Now we're going to move on to student 3, which is a little bit more interesting. So if students 1 and 2 make opposite guesses, right? One guesses blue, one guesses red, and you draw a blue ball, you're going to break the tie. You know that the first 2 convey perfect information, so you've basically just drawn 3 times from the bag, and you can take whatever the majority color you saw was. In this case, blue. Second one, also very straightforward. If they've both guessed blue and you draw a blue ball, you should correspondingly guess blue. The more interesting case comes when students 1 and 2 have made the same guess and you draw the opposite color. As we've established, students 1 and 2, if they announce majority blue, you know that their guesses convey perfect information, right? Your own private information, you draw a red ball, is telling you, oh, you should guess red. But taken cumulatively with these other 2 students' guesses, you probably also want to guess blue. So does your private information even matter? It doesn't. And in this case, when you abandon that red ball, which would tell you to guess red, if you abandon that information and guess majority blue, following what students 1 and 2 have done, an information cascade has begun. If we want to think about student 4, we can consider the case from before that's interesting, where students 1 and 2 have made the same guess. We've seen how student 3 will also make the guess of majority blue. So this is the information you have. You have majority blue, and majority blue, and now you've drawn a ball. What are you going to do? You know that guesses 1 and 2 are perfect, and as we've said before, guess 3 conveys absolutely no information because regardless of what student 3 gets, they are going to guess blue. So now, should you base any of your decisions off of student 3? No, because it doesn't convey any real information. You should base your guess off of guesses 1 and 2, which do convey some level of information. So effectively, you're in the same position as student 3, regardless of what color you draw. And so the best strategy is just to rely on their 2 guesses, the first 2 guesses. And we're going to justify all of this later mathematically. So what does this experiment tell us about information cascades? First, they can occur super easily given the right structural conditions. We saw how, if the first 2 students, they both draw blue balls, what's going to happen is everybody after them is going to continue guessing blue, 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 all the way down. This is very bizarre, but completely rational. Second, information cascades can lead to very non-optimal outcomes, right? If these first two students both draw blue, in the case of a majority red bag, there's a 1/9 chance of that happening, you can get population-wide error, and that's really unfortunate because all of these people have private information they're not able to convey. The third point is that cascades are fundamentally fragile. We didn't see this in action, but even after persisting for a very long time, you can break a cascade. If we're in the same situation where the first two students guessed majority blue, a cascade forms. But let's say in the middle you have two students who want to cheat, right? They draw a ball, both of them happen to be red, and they want to show them to the entire class. Then students in your experiment, they have new genuine information to use. And effectively, you've seen 4 guesses. You've seen 2 blues and 2 reds. So student 52 now has the power to break the tie and make a new guess. And that might form a new cascade. But we want to justify all of these results mathematically, so we're going to talk about conditional probability and Bayes' rule. If you've taken probability theory before, this might be a little bit of a review, but in this experiment, the fundamental question that students are trying to answer is, how likely is it that the bag is majority blue or majority red, given the ball that I drew, given my private information, and the guesses so far? The information that I can infer from other people's guesses, behavior, right? So if we're thinking in terms of probability, the notation that the book uses is PR bracket A, and this denotes the probability of some event A occurring. If you think about it in terms of the sample space diagram, where the entire rectangle is the total sample space of any event happening, region A corresponds to the probability of event A. Conditional probability is what is the probability of A happening given that some event B has occurred? What is the probability that the bag is majority blue given this ball that I have and the guesses so far? We're trying to condition the probability. So this is denoted by PR bracket A bar B, and we can calculate it by thinking about the sample space diagram that you have. It's given by the fraction of region B that's occupied by the intersection of A and B, right? So it's going to be this area divided by the total area of B, because you know that B has occurred and you want to find the probability that A has also occurred. So it's just the proportion of this whole region that is occupied by the intersection. So to write it out mathematically, this is what it looks like. The probability of A given B is equal to the probability of A intersect B over the probability of B. And if you want to find the probability of B given A, it's the same thing, it's just flipped. So we're going to derive Bayes' rule using these two equations. And this is like my chalkboard that I unfortunately cannot use, but these are our two equations from the previous page that we found using the sample space diagram. If we rearrange by multiplying both sides by probability of B, and then this equation multiplying both sides by the probability of A, and then you'll notice that this is equal to this, so we can set the two sides equal to each other. We find this equation. If you divide both sides by B, you can isolate the probability of A given B, the conditional probability that we're trying to find. And this is the formula that we get to come up with. And why is this particular form? Well, Bayes' rule is about relating quantities that make sense to each other. So another way you can think about this, if you're trying to find the probability of A given B, is you're trying to find the probability that a certain hypothesis A is true given some evidence B. So we call the probability of A given B the posterior probability. How likely is the hypothesis given the evidence that you have? And that's a very fundamental question that, a lot of researchers, investigators might try to answer. You want to relate this to the prior probability. How likely is the hypothesis on its own? Without the evidence, how likely is it that A has occurred? The other two terms in this equation, the probability of B given A, we call the likelihood. How likely is the evidence if the hypothesis is indeed true? And the denominator is the marginal probability. How likely is the evidence under all possible hypotheses? And the law of total probability is going to come in handy later. It's not super important, but in terms of marginal probability, you're trying to consider how likely the evidence is under all possible hypotheses, right? So you might consider, let me split up all the ways B can happen by the different possible hypotheses. And then you're basically going to take a weighted average of the probability. You're going to multiply the probability of this evidence given a particular hypothesis times how likely this particular hypothesis is. And you're going to sum all of that to find out the probability of B. So let's apply Bayes' rule. in an example involving yellow taxi cabs. So you're an investigator in a particular city. In the city, 80% of taxis are black and 20% are yellow. There happens to be an accident and you have eyewitness testimony that tells you the cab was yellow. You happen to know that eyewitness testimony is not perfect. Witnesses only correctly ID the color 80% of the time. So now you're trying to figure out, how certain can I be that the cab was actually yellow given that the witness said it was yellow? So we're going to call this the probability that it's truly yellow given that it was reported to be yellow. So let's calculate it. Bayes' rule tells you, this is just a very plug and chug version of this formula, the probability that it's truly yellow given that it was reported to be yellow is equal to the prior, the probability that it's truly yellow, times the likelihood, the probability that it is reported to be yellow given that it is truly yellow, over the marginal, which is the probability that it was reported to be yellow. What are your givens? You know that 80% of taxi cabs are black and 20% are yellow, which translates to these two quantities, right? And you'll notice you can go ahead and plug this in up here. And secondly, you know that witnesses correctly ID the color 80% of the time. So the probability that it's reported yellow when it's truly yellow is 80, and the probability that it's reported yellow when it's actually black is 20%. And we can go ahead and plug these two quantities into our equation up there. You also want to calculate the denominator, and this is where the law of total probability comes in. Either the cab was truly yellow or it was black, and we can break it up like this. So the probability that it's reported to be yellow is the probability that it was reported to be yellow and is actually yellow, and the probability that it's reported yellow and is actually black. And both of these you want to weight them by the probability that they're actually yellow or actually black. And we can plug in the quantities. This is very straightforward math. It's just 0.8 times 0.2 and so on. If you put all of the quantities together, you find out that the probability that it's truly yellow, given that it was reported to be yellow, is only 50%. I think for me that's kind of shocking. It's not super intuitive that it's only a 50% likelihood, but if the eyewitness says that it's yellow, it's just as likely to have been a black cab. So, Bayes' rule can help level our understanding of certain situations, but it can also just help us calculate probability in general. And I do want to point out, even though 50% does seem low, this is very different from the prior, which is that you would only have 20% certainty that the cab was yellow. Now it's 50%. So let's go ahead and apply Bayes' rule to our herding experiment now that we understand how it works a little bit better. So the decision to be made here, you want to guess majority blue if the probability of it being majority blue, given what you've seen in herd, is greater than 1/2. You would guess majority red if, the conditional of that is greater than 1/2. And if it's equal to 1/2, you're completely ambivalent and you're completely ambivalent to either decision. In terms of the experiment setup, you have some priors. The probability that it's majority blue or majority red without any other information is 1/2. And you also know something about the composition of urns, right? The probability of you drawing a blue ball from a majority blue urn is 2/3, and same for a red from a majority red. And correspondingly, to get a red ball from a majority blue urn is 1/3. And these are your likelihoods. So now we can do calculations to justify all of our intuitions. So let's start with student 1. Let's say student 1 draws a blue ball. This is what Bayes' rule tells us, right? We want the probability that it's actually majority blue, given that student 1 drew a blue ball. And we're just going to go through and calculate each of the quantities. The probability that it's majority blue, as we said, is 1/2. The probability that it's a blue ball given a blue bag is 2/3. And now we want to calculate this bottom thing using the law of total probability, right? You want to calculate the probability that it's blue, assuming that the ball is blue, first assuming that it's a majority blue bag, and then second assuming that it's a majority red bag. So the probabilities of the two bags being majority blue or red are each 1/2. And then if you're drawing a blue from a blue bag, that's 2/3. If you're drawing a blue ball from a red bag, that's 1/3. If you multiply all of this out, you find out that the probability that this bag is majority blue, given that you drew a blue ball, is 2/3. So it makes complete sense to guess majority blue if you are student 1 and you draw a blue ball. The calculation for student 2 is basically completely the same, so we're going to go ahead and move on to student 3, which is a little bit more interesting. So student 3, let's say you draw a red ball after guesses of blue and blue. just to keep things interesting. So Bayes' rule is now you're trying to find the probability that this bag is majority blue given guesses of blue, blue, and a draw of red. And as we've said before, because the two guesses convey perfect information, it's effectively drawing blue, blue, and then red, right? So again, the probability it's majority blue is 1/2. The probability that you get blue, blue, and then red, given a majority blue urn, is 2/3 times 2/3 times 1/3, which gives you 4/27. And then we use the law of total probability to calculate the denominator again. So these two quantities are 1/2. Over here, blue, blue, red, as we've calculated, is 4/27. Blue, blue, red in a red bag is just going to be 1/3 times 1/3 times 2/3, which gives you 2/27. And when you put all of this math together, what you find is that the probability that the bag is majority blue, given two guesses of blue and your ball being red, is still 2/3. So regardless of what student 3 draws, they should always be guessing majority blue, because Bayes' rule tells you the conditional probability is still going to be 2/3. And that's how an information cascade develops. So Bayes' rule here in this case helps us justify the results of this experiment. But Bayes' rule can also be used to develop a more general model that we can apply to other situations to model information cascades. So what kind of components do we want in this model for information cascades? Well, first, as we've established, there's going to be some kind of sequential decision, right? Let's call our people 1, 2, 3 who decide in sequence whether or not to accept or reject an option. So that's the decision, whether you accept or reject. We're also going to assume the world has different states that is determined by some unobservable random event, let's say, so there's a probability associated with it that, but we don't know like what caused it necessarily. So either the world is good, which means the option is good, or the world is bad, which means the option is bad. So intuitively, if the world is good, you want to accept. If the world is bad, hopefully you've rejected it so you don't suffer some kind of negative payoff, right? So that's where payoffs comes in. You want there to be a 0 payoff for rejecting. If you reject it, no harm comes to you, no good comes to you. If you accept, though, in a good world, in a G world, you get a positive payoff. Something good happens to you. In a B world, you get a negative payoff for accepting. But it's important to note that the expected payoff for accepting without any information is still going to be 0. So you want the payoffs for rejecting and accepting to be equal to each other, sans other information. Finally, you want to incorporate some kind of private signal, some private information that you know for whether accepting is a good idea or a bad idea. And this is communicated through signals, H and L. H being a high signal that the world is good, and L being a low signal so that accepting is a bad idea. So in a good world, H signals are more common than L signals. You know, it's more likely to be accepting is a good idea. And in a B world, L signals are more common than H signals. This model completely describes the herding experiment, right? If you go up here, there are people making decisions in a sequence, the students deciding whether to accept that the bag is majority blue or reject that the bag is majority blue. The world has different states. Either the bag actually is majority blue or it's not majority blue and it's majority red. There are some payoffs which we haven't strictly established, but let's say if you guess wrong, you get shame. If you guess right, you get a lot of glory, something like that. And then private signals, the private information you have is the ball that you draw, right? The ball that you draw that you don't show to anybody else. And if it's a majority blue bag, you're going to be drawing more blue balls. So the blue ball is the signal H. So let's formalize this model that we've developed and attach some notation. So in terms of the world having some kind of probability associated with it, we want the probability that the world is good to be some probability P and the world being bad to be 1 minus P. So these kind of exist together. There are also payoffs, right? And the payoff is 0, again, for rejecting. There's a positive payoff for accepting in a G world, V sub G, which is greater than 0, and then a negative one for accepting in a bad world. And this last line can be summarized by this equation, which just tells you the probability that it's good, the expected payoff is going to be equal to V0. In terms of the private signals, we're going to be using some conditional probability notation. The probability that you get an H signal, given that the world is good, is going to be some quantity Q, which is greater than half. That's pretty important, that it's greater than half. And correspondingly, the probability you receive a low signal in a good world is going to be 1 minus Q, which is less than half, and vice versa, which is summarized in this table over here. You can see in a bad world, it's more likely you get an L signal. In a good world, it's less likely that you get an L signal. So, how can this model help us understand how people make decisions? To apply it really simply, let's just go, how should you make decisions based on only your private signal? This is not yet a cascade, we're just trying to understand how this kind of might apply. You have some information, you have your own private information. Let's just say, for the sake of this example, that it's an H signal. You get an H signal. How does your payoff change? So we said before, this is the expected payoff for accepting a decision. It's the probability that it's a good world times the payoff for accepting, the probability that it's a bad world times the payoff for accepting in a bad world. So this is as we said. Your payoff changes because now it's not just the probability that it's a good world and a bad world, it's the probability that it's a good world given your private information, and the probability that it's a bad world, again, given your private information. So using Bayes' rule, this is just a very straightforward plug and chug. We can split it up into the prior and the likelihood, divide it by the marginal. You can use the law of total probability to split up the marginal into these couple of cases, split it up over all possible hypotheses, and then plug in the values for P and Q that we've established above, right? We said that the probability that it's a good world is P, right here. The probability that you receive a high signal in a good world, we called a quantity Q. And then this is just the same plug and chug for G's, for H given G, for B, and H given B. Now, what do you know? We said before that Q is greater than 0.5, right? A simple substitution here tells us that if we replace if we replace 1 minus Q with Q, you know that Q is greater than 1 minus Q. So this entire quantity, this whole denominator, is less than Q, right? So this tells us that if the denominator is less than, then the whole fraction is greater than. This is greater than PQ over Q, which is equal to P. So what have we found? We found that the probability that it's a good world, given your signal, is now greater than P. And how does this help? That means that the payoff is positive. You'll notice that this is a positive quantity and this is a negative quantity. So if this increases from P to something greater than P, then your payoff as a whole increases. So your payoff is positive and therefore you should accept. So how should this operate for multiple signals if we try to adapt this to a more general information cascade? Well, let's suppose you're receiving a sequence S of independently generated signals, a mix of A, high signals, and B, low signals, in some kind of order. And notice here that you're not receiving information about what other people have done if they've accepted or rejected. You actually have the signals. So this is kind of like our case of receiving perfect information from the people beforehand. So you know these signals, you have a sequence of signals, and they're independently generated. The question we're trying to answer now is, how does the probability of it being good given this signal compare to the original probability of it being good? And it's going to be a similar calculation to before. So if this new conditional probability, if this posterior probability is greater, you're going to want to accept and otherwise reject. We're going to analyze this using Bayes' rule. So this is a slightly more complicated calculation, but the probability of G being a good world is just P, as we've done before. The probability of getting this sequence, given that it's a good world, can be calculated. We said that they're independently generated signals, right? Which just means it's not going to come in some kind of associated batch. They're independently generated, and in probability, you can multiply things that are independent. You can multiply the probability of events that are independent, which means you can just multiply the probabilities. And you know that there are A high signals and B low signals, which means it's just the probability of it being a high signal Q multiplied A times, so Q to the A, and then B factors of 1 minus Q for low signals, which is just 1 minus Q to the B. So the calculation of the likelihood is this, it's pretty straightforward. It's Q to the A times 1 minus Q to the B. For the marginal probability, again, we split it up using the law of total probability, and this is just a very straightforward plug and chug for what happens if the world is actually good, what happens if the world is actually bad, and you're going to go through and proceed like this. Putting it all together, you get this fraction. It's a pretty hefty fraction and you want to understand what's going on. So let's make a replacement. We're going to sub in this thing in orange. We're going to replace this 1 minus Q to the A and Q to the B with Q to the A and 1 minus Q to the B. So you'll notice we swapped the exponents. And I don't actually know how this changes this relation, but I'm going to swap this in to simplify the fraction and then figure it out. So if you do plug this in, you'll notice this term, this right here, is now the same as this right here. So P plus 1 minus P is just 1. So this entire quantity simplifies to P if you make this substitution. So now the question becomes, how does making the substitution change the value of my fraction, right? Like, does it make the denominator bigger or smaller? We can do this calculation and notice that Q is actually greater than 0.5. So if A is greater than B, then you're raising a bigger thing. This is Q, this is 1 minus Q, this is bigger, this is smaller. You're raising a bigger thing to a higher power and a lower thing to a lower power compared to what it was previously. So in this case, the denominator is greater, right? Like Q is raised to a higher power now. If the denominator is greater, the fraction gets smaller. So now the posterior probability of it being a good world given the signal you have is greater than the original prior probability that the world is good. In this case, this makes your payoff positive, so you should accept. If A is less than B, we can do a very similar calculation and find that the denominator is smaller, so the fraction increases, which means that your payoff is now negative, so you should reject. If they're equal, everything stays the same, so you can accept or reject, do whatever you want. This calculation tells us that the decision rule here is use the majority vote. If A is greater than B, if you're receiving more high signals than low signals, you should accept, right? The payoff is positive, and that makes sense. If you have more high signals that it's good, then you should accept. And inversely, if you have more low signals than high signals, if B is greater than A, you should reject. It's all fairly intuitive. So what we've done here is develop a model for making decisions, whether to accept or reject, and it's based completely on the number of high and low signals that you get, and you should just always follow the majority. So how does this model help us in an actual sequential decision-making process? Let's walk through it. And you're going to find that actually a lot of this logic follows the intuitions we had about the herding experiment from the beginning. So what is person 1 going to do? Person 1 is going to follow their own private signal. If person 1 receives an H signal, they're going to accept because they have more H's than L's, and correspondingly an L would make them reject. So they follow their own private signal, and person 1's decision then conveys perfect information about the signal they received. For person 2, it's the same. They should follow their own private signal. Why? If they get a signal that's opposite from the decision that person 1 made, they're completely ambivalent. We said they should just follow their own private signal. If they get a signal that corresponds with the decision that person 1 made, well, it's very easy. They should just go with the majority again. For person 3, if persons 1 and 2 made opposite decisions, then they should be the tiebreaker, right? Person 3 is still, again, going to follow the majority signal, which is the rule that we established. And here the signals are the 2 inferred signals because persons 1 and 2 are conveying perfect information through their decisions, and the third signal is their actual own signal. So in the first case, right here where they make opposite decisions, person 3's decision conveys perfect information. If persons 1 and 2 made the same decision, regardless of what person 3 has, the majority is going to be what they both announced, so an information cascade has begun. What about for person N? If an information cascade has not yet begun, that means the decisions of everybody else before you conveys perfect information, right? It corresponds directly with the signal that they received. We're going to consider that case where an information cascade has not yet begun. Let's let A be the number of acceptances so far and R be the number of rejections before you. And again, these acceptances and rejections correspond directly to the signal that they received. There are 3 cases. The first, let's say before you, A is equal to R. There is an equal number of acceptances and rejections, which means that the signal you receive is the tiebreaker. And as a result, you should follow your own signal when you're making your decision. In the second case, if the number of acceptances and rejections differs by 1, then either your signal is going to make you indifferent, meaning that, let's say there's more acceptances than rejections right now. If you get an L signal, then it'll make you completely indifferent from what to do. So you'll just go ahead and follow your low signal and reject the option. Or it's going to reinforce the majority, right? If you get an accept, if you get a high signal, it's going to encourage you to accept, which goes along with the majority. So in either case, you should follow your own signal. In the third case, if A and R differ by 2 or more, regardless of the signal that you receive, it's not going to outweigh the previous majority. If there are so many more A's than R's, even if you get an R, it's not going to make there be more R's than A's. So in either case, you have to follow the previous majority. Therefore, your decision stops conveying information, and this is where an information cascade begins. So to understand this a little bit better and just summarize it, there's this graph you can look at. And you can see the bounds at 2 and -2. So what is this graph saying? As long as you're staying between -1 and 1 for the difference between the number of acceptances and rejections, there will be no information cascade. Everyone, through their decision, is going to be conveying perfect information. But as soon as this quantity is 2 or more, it crosses this line or it crosses that line, and a cascade is going to go on forever. Obviously, it's very hard to stay within +1 or -1 forever, and actually the probability of this goes to 0, so it's extremely likely that, or it's basically guaranteed that you're going to find matching signals as n goes to infinity. So what this tells you is that inevitably a cascade will happen if people are making decisions in sequence like this, which is unfortunate, but the thing to keep in mind is that obviously this is just a simple model. It's an oversimplification of reality, but it still does offer some lessons for us. And these lessons are, first, cascades can be based on very, very little information, right? Only the things that happen pre-cascade are used when people are making their decisions, and only this information can be used to influence the population. After a cascade happens, the private information isn't being used anymore. If you think back to the student's example, as soon as the first 2 people guess blue and everybody else is going to follow them, everything that happens after these first 2 guesses, all of that private information is hidden. You have no way of accessing it. Second thing, as we've discussed, cascades can be wrong and lead to non-optimal outcomes. And the third point, as we've said before, is that cascades are fragile. People who receive just information that's slightly better, if they gain a slight edge of genuine information, they can overturn long-lived cascades, right? So what's the overall point? Basically, you should be careful about drawing conclusions about, the best behavior or the best decision to make based on the behavior of a crowd. And, some common misconceptions, if you think about something like The Wisdom of Crowds, a pop science book, where the author claims that, people who guess the number of jelly beans in a jar on average, they're very good. The average is very close to the actual number. You have to remember this applies to independent decision making. And it's not where people are making decisions in sequence. Everybody comes to it independently. In that case, people might be good at making decisions, not so much in a sequential decision-making case. And second, where this might apply in your own life is with group decision making or, collaboration between people. These are especially susceptible to cascades depending on who goes first, what kind of information they have. And the way you can avoid this is by working in smaller groups, trying to come to partial independent conclusions first. And the third point is it's a global pandemic right now, so crowds are behaving in a certain way, and just make sure you're not falling victim to an information cascade. And that concludes my presentation. Thank you very much for listening.